Hello everyone, welcome back to my channel, Predicting the Future. Today we're going to talk about Boost coroutines. So for those who don't know what is coroutine, if you come from C# or you come from JavaScript, you can use await and async keywords to avoid using callback functions or nested callback functions or splitting a logic into smaller functions. And and that's coroutine, and that's what we are gonna talk about using Boost coroutine. So Boost coroutine is a little bit different than C++20 coroutine, but they are very similar. So as I just mentioned, the coroutine makes asynchronous programming much easier to read. And let's learn that by example. So here I define a couple of coroutine functions. The first one is called call push fun1, and the second one is call pull fun1. So as you can see that I'm using the Boost Coroutine2. So I'm just importing the namespace, and this two function has one common parameter, well, similar parameter. The first one, which is yield. So every function has a yield, but it's different. The type is different. So this one, the push fun1, I define a coroutine int push type reference, and this one I'm defining a coroutine int pull type reference. So the coroutine int means that I'm either sending an integer value back to the caller or receiving an integer value based on whether it's a pull type or push type coroutine in Boost. And I defined two more main test functions. So the test function, one is called test call pull fun1, and the other is test call push fun1. So the test call pull fun1 is we are defining a pull type coroutine, and the other one we are defining a push type coroutine. When we define a pull type coroutine, the function we are calling that is responsible for this routine, the logic of this routine, is a push function. Is a call push fun1. So a pull type corresponds to the push fun1, which means that a pull type coroutine must have a push type yield as its first parameter, and the other one is the same. So if we have a push type coroutine, then the push type function must have a pull type yield as its first parameter. So that's how we define coroutines. So let's first look at the pull type coroutine. So we define a pull type coroutine. The int here is telling us that the function called push1, the coroutine function, will be sending data back to us, back to our main test function, and we're going to consume that value from this coroutine. And so once we define this pull type coroutine, we're gonna run right away. So as you can see, this pull type coroutine, the first parameter is the coroutine push type yield. The second one we define it by ourselves, and it's not required by any standards or by the library, but we just want to show you guys how you can pass parameters to coroutines. So I pass integer a, and then I'm gonna loop over from 0 to a minus 1. And when I define this pull type coroutine, I use the std bind to bind this function with that integer a as the second parameter, and leave it the first yield parameter as a placeholder. And so once we define this variable resume, this coroutine function called push1 will be called right away. So this function will be called when we are at line 32. And if this function goes into this for loop, and then we're gonna see a coroutine push being printed out in the console, and then we're gonna this function will come to the next line 11, line 11, and call the yield and give the value I back to the caller. What this yield does is that it will pause. So the function call will be paused in here. The context will be saved in the heap. It's not on the stack anymore. So the context, if there's any local variables, including the parameters, the function parameter, will be saved in the heap, and the function context will be saved, and the control of the workflow, the whole logic will be returned back to the caller, which means that so once we are syncing here, the function is called, and then yield was called, and we come back to this next line 32. So the control, the workflow, the business, the code logic comes back to the caller. The function was the context of the function we're calling has saved, and it's paused at this yield function. So once we come back, we check whether this coroutine has finished by a boolean, because this coroutine has overridden the boolean operator to tell us whether true or false. True is that this coroutine is still valid. We can still continue calling this coroutine. Or false means that the coroutine is finished. So if it's true, that is, we can still continue, then we can get a value from this coroutine, which is sent by the yield, and then we call the coroutine again, which is resume, and then the bracket is what this does is that this will pause this control at this point 35, and the control goes back to where we have left at yield in this function. So the context saved. So here is also a context saved. So once we resume, the function, the stack will be saved in the heap rather than on the stack, and the function was paused in resume function in line 35. So the function logic return back resume back to this function where we last calling yield, and continue the logic after yield. And then after the next loop, we call the yield again. We send another value, which is 1. Last time is 0. This time is 1. And after calling yield, this function pause again. The context was saved in the heap again, and the control of that workflow back to the caller where the resume was called. So last time resume has lost its control. Now resume after the yield from that function, the control back to here, and then that will go to line 36, and then line 33, and continue the while loop, and then we get the value 1 from here, and then resume again. So you see, that's coroutine. So we basically switching context between two functions. We can so this is like we define a coroutine. We want to wait for the network to send us data, and rather than giving a callback function, have split the logic into let's say the while logic into a separate function, which will be the callback function that we want to use for receiving when it's finished. We don't need to separate that anymore. So the logic is complete. It's in one function. We don't need to split that logic into smaller functions. And once that network has received data, it will yield the data back to us, and then we're gonna receive that data in the same function. So that's the coroutine, the benefit of coroutine. We made the code much easier to read. So another one is still, so let's see the next line here. This is, the next line is still pool type coroutine, but this time we're using a for loop. We're using the C++ 11 new context, a new syntax for for loop. But see here, so why we can do that? Because pool type has an iterator. So when we define the pool type, the first one we call here, and then when we go to the for loop, we are iterating using the iterator from the pool type to iterate every course. As long as the call is now finished here, we can, as long as the U still have value to send us data, the iterator will plus its iterator to continue calling the coroutine and get the data, and call the get value out of the coroutine. So here it's a code it's all because of the code iterator defined in the coroutine. So next one is push type. So as I mentioned earlier, if you have a push type coroutine, the function, the logic of that push type coroutine must have a pool type U as its first parameter, and the logic is very similar. So the only difference is that the push type coroutine, once you define that, the function was not called again. That makes sense because the push type, we haven't sent data to that function yet, and that's what we are doing here. So we define the push type coroutine. We want to send some data. We iterate over this vector. Then we use the coroutine sync to send the data I to the coroutine function called pull func1. And once we sync, the logic in this main test function will pause at this line 45, and the control of that business logic goes back to the call pull func1. And in this function, as you see, we have a U. We check whether the U has finished or not. If it's not finished, we can get the value and we can call the yield again. So and also you can see we have a local variable in this coroutine, and because the coroutine stack was not in stack data, it's not in stack memory, it's in the heap. So those are saved in the heap as well. And every time the context is switched, the heap will be restored, and then so the yield, every time the yield will be using the previous values we set for the run. And so that's what it is for coroutines. I hope you guys like it, and bye.